Welcome to our next installment of ELE 475. Today we are going to be continuing our discussion of advanced cache techniques. And one of the big things we're going to get into is talking about how to build out-of-order memory systems. So what I mean by out-of-order memory systems, basically I mean you can have memory operations out at the memory system, but they execute out of order. And you can mix this with the in-order processor pipeline or an out-of-order processor pipeline. It's the designer's choice. Both sorts of designs have been built and have been successfully built. But where this is important is it allows you to effectively get more memory parallelism, because you can have transactions going out the memory system in parallel, and the processor could continue an overlap computation with the memory. Just to recap from last lecture, we have a revised agenda here, with all of our different cache optimization techniques or advanced optimization techniques. We talked about pipelining caches. We talked about adding a write buffer and a coalescing write buffer last lecture. We talked about the reason and the motivation for multi-level caches, so 2-level caches, 3-level caches, maybe even 4-level caches backed by main memory. We talked about having victim caches, which were extra little highly associative caches that you could put next to a low associative cache or something like a direct mapped cache. And effectively, this can increase your performance quite a bit. Because once you sort of miss in your direct mapped cache, you can go out to your victim cache, and if the victim cache may have the data you're looking for, and this gets over small numbers of lines which are highly contended and might blow out, if you will, the number of ways or the amount of associativity you have in your cache. We talked about hardware and software prefetching, and this is where we stopped last time. We stopped at hardware and software prefetching, and today we have a couple extra topics. We're going to talk about how to bank your cache as a technique to get more bandwidth. The easy technique to get more bandwidth is just to put multiple ports on your cache, but that gets quite expensive because you have to duplicate your possibly your sense amps. You probably have to duplicate the write logic, and in the worst case, you may have to duplicate the storage space. In today's lecture, we're going to talk about some software optimizations that the compiler can do. We're going to start off by talking about some software optimizations that are easy to do without transforming the code too horribly. And then we're going to talk about some that actually require some pretty heavy lifting with respect to code transformations and what you have to do to reorganize the code, still in valid ways, but by doing such, you can actually have better memory performance and better cache performance. And then we're going to get to the meat of today's lecture. We're going to be talking about non-blocking caches, or sometimes called lockup-free caches, or sometimes called out-of-order memory systems. Then a couple potpourri at the end here. We're going to have critical word first, which basically means that when you go out to the memory system, you ask for the word that you need most urgently, and the memory system will give that back to you first. And this allows you to restart quicker. And then there's a very similar idea, but possibly easier to implement, called early restart, which instead of asking for the memory system to return the data in a specific order and taking advantage of that, instead what you do is the memory system gives you back the data in order, or whatever the canonical order is that it expects to give it back to you with. But when the word shows up that you need or you're stalled for, you just restart the processor pipeline. So if you're asking for one word out of a huge cache line and it happens to be the second word in the cache line, you don't have to wait for the whole cache line to get loaded into the cache. But this has some extra complexity. And finally, we're going to talk about way prediction. Way prediction, we touched on it a little bit when we were talking about some of the instruction issues in superscalars. But we're going to talk about a little bit more in detail here, where way prediction allows you to predict where to go find either the next piece of data you're going to go access or the next instruction you're going to go access. And this is important if you have a multi-way cache. In a direct map cache, there's only one place to go find it. In a two-way cache, there's two places to go find it. And if you check both, you could try to do that in parallel. That probably wastes a bunch of power. Or what we can do is you can predict that, let's say it's in way 1, or you can predict that it's in way 0. And using that prediction, if you have high prediction accuracy, you may only have to fire up half your cache. Or if it's on your critical path, you don't actually have to do 2 comparisons or 3 comparisons or 4 comparisons, however high the associativity of your cache is. So let's go take a look at banking strategy and multi-porting our caches. This is a little bit of recap. I think we talked about this briefly during last lecture, but we're gonna continue on with that. So here we have our two-way issue processor pipeline. You have a program counter reads in the instruction cache. You have your instruction registers. And what's interesting about this is in this pipe, we can only execute 1 memory operation per cycle. Well, that's a limiter. Let's say you want to execute 2 memory operations, or 3 memory operations, or 4 memory operations that are all independent of each other. What do you go about doing? Well, in our 2-issue pipeline here, logically what you want to do is you want to somehow put the data path on both pipelines and remove this restriction of where you can execute memory accesses, in which pipe you can access memory accesses from. OK, that doesn't sound too horrible until we go look at the implementation of this. So we can go and have a true multi-ported cache. So if a true multi-ported cache, if you think about the decoding logic on a read, we're going to have to at least duplicate that decoding logic. Likewise, if we want to actually execute 2 writes at the same time, we're going to have to duplicate the row decoders for that logic. And a lot of times how people actually go to implement this is they basically duplicate the entire cache to get an extra port for a variety of reasons. It could, the area increase could be large, and it could even be double for a 2-port read and a 2-write port sorts of cache. So they don't even share the storage data. But that's like only a little bit of the problem. The other problem here is that it also increases your hit time in your cache. And no one likes increasing hit times in caches. Now, why does it increase the hit time? Well, unless you, for instance, duplicate everything, if you try to share some of the logic, you're basically going to increase the loading on the readout of the cache here. And by increasing the load, or this is going to have slower drive strains, you will probably increase the time. And you can go look in something like Cacti, which is a tool from HP, which has different cache configurations. And you can see that adding a second port is usually the last thing in the world you want to do when you're doing a processor design. It ends up being really quite expensive, mostly in terms of area and somewhat in terms of timing. So can we do better? Well, maybe yes, maybe no. So one thing you can think about doing is instead of actually having a true dual ported cache, can we have a pseudo dual ported cache, or a cache which has the same external interface? So if we sort of cut out here in the middle, we have 2 addresses coming in, 2 datas coming out. It looks the same, but instead, we actually put something else in the middle here. What do we put in the middle? Well, we actually put 2 banks, they're called, of our cache. And the first bank is half the size of our cache, and the other bank is half the size of our cache, and they're both single-ported. What this is relying on is if you have statistical memory accesses that have some good pattern to them, the probability that you'll actually end up routing 2 memory addresses to the same bank and get what's called bank conflict will be quite low. And instead, the probability that you actually go to 2 different banks will be high. Now, you might say, well, bank conflicts sound pretty possible to happen. This is sort of the naive drawing here. when people go to build these things for large caches, you'll actually have many banks. And then let's say and if you have more banks than the number of ports you have, you can make a decent argument that the probability you're going to get a bank conflict ends up being quite low. Or the probability that any two random addresses will end up going to the same bank will be low. Now, let's talk a little bit about addressing and how we do this assignment of addresses to banks. The most basic thing is you maybe low order interleave it. Or you could try to high order interleave it. So one of the questions that logically comes up here is, which is better, low order or high order interleaving our banks? Anyone want to take a guess on this one? So when I say low order, I mean use the low order bits to hash into which address bank or which bank you go into. High order leaving, you use some high order bits. Or maybe middle order interleaving, use some middle order bits. What would you choose if you were a designer? So this is a good insight. So if we think of something like we're accessing an array, and we're trying to stride through the array. So we're striding through the array. The high order bits of those accesses are all going to be the same. So if we have high order interleaved bits, all the high bits are going to all be the same, and we're going to get bank conflicts. They're all going to go to, let's say, bank 0 all the time. And therefore, our cache, which we were trying to have more or higher throughput, didn't get any higher throughput. OK, now I'm going to give you a counterexample. Counterexample is, let's say you are striding through an array, and you have an array of structures. Pretty common thing to do. And the structure is, let's say, 120 bytes long. And we go and access the first byte in that 128 byte structure in a loop. Are the low order bits of the address the same between all of those? Yeah. So that can be problematic. Now our high order bits are the same, and our low order bits are the same. What's changing in that example? Some medium bits, some bits a little bit higher than the low order bits. So more of what I'm trying to get across here is that you have to be very careful about how you do the bank interleaving. If you have naive hash functions, or naive functions which assign address to a particular bank. And you may not want to even have, you can think about having more sophisticated hashing functions or assignment from address to bank. But if you go to do that, this is on your critical path of your memory load. So you may not want to have a complex hash function there. So you might want to just take some middle order bits. You might want to take some low bits and some high bits for your bank assignment. It gets a little challenging here. You probably don't want the highest order bits, definitely, because in most systems, all those are always, let's say, 0 or something like that. It's very unlikely that your higher order bits are something important, usually, unless you're sort of accessing the stack where those are usually 1, all 1. So I have another, I think we talked about most things on a slide. Benefit, we're trying to go for high throughput here. Bank conflicts, we talked about how you can get a bank conflict. We talked somewhat how you can avoid bank conflicts by having more banks than you have ports into the ported structure. And that's just from a statistics perspective, if you have, let's say, a 32, your caches, you have a 32 kilobyte cache, and each bank is 1 kilobyte or something like that, then all of a sudden you have the probability that you have 2 ports trying to access one particular bank. It's kind of like a birthday problem. So it's not, or it's the trying to find if 2 people have the same birthday, because it's not quite easy probability to go figure that out. But it's quite low because it's roughly, 1, what is this? It's probably 32 times 1 over 32 times 1 over 32. So it's not the lowest thing in the world, but it's possible to actually reduce the probability that you have a bank conflict with random accesses. And if you have a better hash function, of course, you can do better. Extra wiring. So what do I mean by extra wiring? Well, in our previous design, we didn't have these sort of crossover paths. So what this really turns into is a mux here, a multiplexer there, a mux here and a mux there for the address paths. So this adds extra wiring, extra delay by banking. And one of the bigger challenges of the extra wiring for going to multi-banked memories is it'll shrink the bank size or shrink the memory size. And if you traditionally sort of look at memories, they like to be larger. You can amortize the overheads a little bit better of the, for instance, the sense amplifiers at the bottom of the memories and the row decoders and the column decoders if it's bigger. Because, for instance, the row decoders and the column decoders will roughly grow as the log of the size, or the log of the number of bits or something like that. But if you make each of your caches really small and you have multiple of them, that overhead gets worse. So you have to have more sense amps, more row decoders, more column decoders. So it's something to think about. But usually that's relatively small and you're willing to pay that, unless you get some really funny aspect ratios. So what I mean by really funny aspect ratios is if you want to have your, if you shrink the cache too small, so if you have, I don't know, 256 byte caches, and the readout width is, let's say, a byte, you get this very long and narrow cache. And you can try to sort of use column addressing or something to sort of squish that into a more square form factor. But sometimes if you shrink your bank size too small, you get very funny aspect ratios or very long, skinny RAMs that don't fit well into designs. OK, uneven utilization. So what do I mean by that? Well, what I mean by that is just like you can have bank conflicts due to the addressing of the hashing scheme, you can also have a pathological case where all of the interesting data is stored in one of the banks. So let's say, going back to that example, you use low order interleaving to the lowest order bit of the address, which is not the offset, we'll say, to choose between bank 0 and bank 1. But it just so happens the program pads out all of its data structures such that that bit is a constant of 0, basically, for all the useful arrays you're trying to access. Well, what that'll do is it'll locate all of the data lines in bank 0. Well, we just took our big cache and cut it in half because we've effectively placed all of our data over in this bank. So we're getting uneven data utilization. So we get uneven bandwidth utilization and bank conflicts, but we can also get uneven data utilization. These sometimes go together, though, the bank conflicts and the uneven utilization. Because if you're accessing something a lot and it's in bank 0, that means it's probably stored there. So you have uneven storage patterns also. Questions so far about banking, why we want to bank? This is a pretty common thing to do. So a good example of this is if you go look at the Niagara processor, which is a Sun microprocessor that has, the first Niagara had 8 cores. And if you go look at their cache structure, they had 8 banks of the cache. So it was a relatively heavily banked cache in their last level of cache. If you go look at something actually like the multi-core Intel chips out there, they even have more banks. Actually, I think I saw one once where it was the 32 megabyte last level cache for the Intel Itanium 2 had some incredibly large number of banks. I think it was either 32 or 64 banks in their cache. And they were wide also. So they had lots of bandwidth going through that cache. OK, so if we go look at our cache banking, what this really, really helps here is we're increasing the bandwidth. We might actually be hurting some things. We might be hurting the hit time a little bit. Miss rate, miss penalty shouldn't change. The cache size is the same. We haven't effectively increased or shrunk the cache size. Even if you get lots and lots of bank conflicts or even if you have poor utilization, that's still not actually affecting your miss rate because you would have been conflicting in the same size cache. Logically, you could draw a box around it and it would be the exact same thing. It's just that happens that, if you were to have it not be a banked cache, you would have every other line be in the contested ones or something like that. So just having better memory layout is good all around.